Okay, so section 4.1, vector space and subspace. Now, before we talk about vector space and subspace, think about what is the meaning of space in a common day-to-day language. So we know that space means in common day-to-day language, it is an area that is free to occupy. So it's a space, okay? Area or region, some region that is free to occupy. And what is the space of vectors? So in the day-to-day language, simple language, common sense, then space of vectors probably maybe an area that is free to occupy by the vectors, right? By the vectors. But in the mathematical language, okay, in mathematics, vector space has a broader meaning. Okay, vector space is not just a space occupied by vectors. It is actually a mathematical structure formed by the vectors and certain rules, we call it axioms, to handle these vectors. Okay, so in other words, vector space in mathematics has in a much more broader meaning. Okay, it is a mathematical structure, and if we are given some vectors, then if those vectors satisfy all these 10 conditions, okay, to be more precise, what is the vector space? Well, a vector space is a set, non-empty set V of objects called vectors, on which we define two operations, addition and multiplication by scalar, and it will satisfy all those 10 conditions. If the objects from this set V satisfy, checks all of these 10 conditions, then that space is called the vector space. Now let us look at a few examples. Now I want you to check quickly what are those axioms, okay? The first condition is if U and V is in V, then their sum must also be in V, in the same set. U plus V equals V plus U. So it must satisfy the commutative property of addition. We call it commutative, okay? You just switch the position and still they are equal. U plus V plus W equals U plus V plus W. It is called associative property of addition. So here we have an association group of U and V, and we added that group into W, or if you have group of V and W and you added that U, they must be equal. If they are equal, they must be equal. Axiom number 4, there is a zero vector 0 in V such that U plus 0 equals U. If you add 0 in the vector, that will not change its value or change its, it doesn't change that vector. It will remain the same. We call it additive identity. For each U in V, okay, see V is a set, V is a space, okay, and U is its objects. U, V are the vectors, they are objects. And if you take this U from V, there is a vector with negative sign, with opposite sign in V such that U plus negative U will be 0, and so on. So if it satisfies those 10 conditions, then we call it vector space. So remember, over and over again, we have to prove whether the given space is a vector space or not. In that case, first of all, what we will do, how we prove is that we need to remember that there are 4 entities involved. in the vector space. Okay, 4 things. 1, a set of vectors B, and we consider set of scalars, and then we have a binary operation, vector addition, denoted by this sign, addition, and a scalar multiplication denoted by dot. Okay, this one is vector addition, and this dot represent vector multiplication. But sometimes the addition may have a different meaning than usual. Okay, please remember, sometimes this plus sign may have a different meaning. Sometimes it can be 2 plus 3, maybe 8. And sometimes 2 plus 3, maybe 5. It depends on how we define this symbol, addition. Okay, it may, what I'm saying is it may have a different meaning in some situation. You need to be careful. All right, so that's the thing. Now, some of the example is R2 is a vector space, because we'll prove later that R2 satisfy all those 10 conditions. R3 is also a vector space. Rn is also a vector space. The set Pn of all the polynomial of degree n less than or equal to n also is a vector space. The set M by n of all M by n matrices also is a vector space. So we'll prove that, because they are vector space because they satisfy all those 10 conditions. Now let's look at one simple example. We want to show that R2 is a vector space. It means we have to show that the space R2, I think you know what is R2 means, right? R2 means this space, this Cartesian coordinate. It is a vector space. That's what we're gonna prove now. Okay, so how do we prove it? Remember, we need to define 4 things here. We need to consider 4 things. Let us consider 3 vectors. Let U, V, and W are the 3 vectors. So U, if U is in R2, then this will be of this type, right? Because there are 2 entries, because it is R2. If V is in R2, then you can write V1 and V2 and W1 and W2. So we consider 3 vectors. All belongs to R2. Okay. So that's one thing. And now we consider some scalar. And let C and D be scalar. Okay. Or you can say C and D belongs to R. You can write this belongs to R. You can write this way too. They are scalar. And now we need to check those 10 conditions. All right. We need to check 10 axioms. If it satisfies all those 10 axioms, then this is a vector space. Otherwise, it is not. So let's work axiom number 1. In axiom number 1, U plus V. Remember here. So axiom number 1 is the sum U and V, which is denoted by U plus V, must be in V. We call it closed under addition. So let's see. We know that U is in R2 clearly, and V is in R2. We need to prove that U plus V is also in R2. Okay, let's see what happens. U plus V. U is U1, U2, plus V is V1, V2. And if I add them, I'm going to get U1 plus V1 and U2 plus V2. Clearly, this belongs to R2, right? Because there are 2 entities only. So this is not in R3. This is just a point in R2 in 2 dimensions. So this clearly belongs to R2. So condition 1 checks. Now let's look at second property, second axiom. What is second axiom? Let's look at that. Second axiom is u plus v and v plus u must be equal. We call it commutative property. So let's look at that quickly. So let us find u plus v. We already found u plus v, which is u1 plus v1, u2 plus v2. And let us find v plus u. V is v1, v2 plus u is u1, u2, which gives me v1 plus u1 and v2 plus u2. So we can actually write this because this is addition. If it is a subtraction, then we cannot switch it. We know that 2 plus 3 equals 3 plus 2. We can write this way, right? So we can write u1 plus v1, u2 plus v2. They are equal. So what we prove here is that therefore u plus v equals v plus u. So condition 2 checks. In the same manner, we have to prove all those 10 conditions. Okay, guys, I think you can continue this by yourself. So try to complete all those 10 conditions, all right? Axiom 3 is associative under addition. So associative under addition is u plus v plus w. So we need to prove that this equals, okay, let us look at what happens. U plus v. U is u1, u2 plus v is v1, v2 plus w is w1, w2 equals. Remember, because of the bracket, we have to use the, order of operation. Recall from your elementary school. So we have to complete this side first. So you're going to get u1 plus v1, u2 plus v2 plus w1, w2, which can be written as u1 plus v1 plus w1, u2 plus v2 plus w2. And now let's see, u plus v plus w. So we have a different association now. So what it means is u is outside of the bracket, and then inside the bracket we have v1, v2 plus w1, w2. Now u1, u2 plus, we need to do the operation inside the bracket first. So we're going to get v1 plus w1, v2 plus w2. So if I combine them together, I'm going to get u1 plus v1 plus w1, u2 plus v2 plus w2. Okay, and so they are equal, as you can see clearly. Therefore, u plus v plus w equals u plus v plus w. It checks. Okay, now 4. Property number 4, it's a 0 vector is there. So there is a 0 vector. There is a 0 vector in R2 can be written as 0, 0, right? Clearly in R2, we know that it's origin. So this 0, 0 definitely is in that space because this also is in R2. And such that if I add u plus 0, so what do I get? U plus 0 is u1, u2 plus 0 means 0, 0. And so you're going to get u1 plus 0, u2 plus 0. So you're going to get u1, u2. So clearly, therefore, what we notice here is that u plus 0 equals u. So this condition also checks. And condition 5. For each u in, you know that we use this symbol for belongs to. So I think you already know that. When I write this way, what I'm saying is this sign read as belongs to. So for each u belongs to R2, there is a vector negative u in R2, because you see, if there is this point 1 2, then there is another point which is -1 and -2, right? So there must be -1 and -2 must be there somewhere here. So that's the point. So -2 also belongs to R2. There is a vector negative u in R2 such that u plus negative u. Let's see what happens. Do I get 0? u1, u2 plus negative u1, negative u2. And if you combine them, you're going to get 0 and 0. So which is a 0 vector. It's called additive inverse. So this also checks. If you want, you can write simply 0. Okay, this also checks. Okay, guys, 5 property we have already proved. Now, others, I think I'll do one more and I leave others to you. Let's look at 6, property number 6, axiom number 6. What is axiom number 6? Let me go all the way there. The scalar multiple of u by c, denoted by cu, is in V. Okay, so we call it scalar multiplication by u. I mean by c. Okay. Let c be a scalar and u already belongs to R2. We know that. We consider that. Then cu clearly cu also belongs to R2. So it also checks, because remember, we are talking about the whole space here, R2, let's say. And suppose we have a point 1 2, for example, and let's say this is my u, and let's say my c is any constant, let's say 3, for example. So when I do cu, I'm going to get c 1 and 2. C means 3, 1 and 2. So that's going to give me 3 and 6. And clearly this 3 and 6 also belongs to R2. It doesn't belong to R3. It doesn't belong to R4, right? It must belong to R2. That's what it is. So if we have a scalar c and then we have a vector u, and if we multiply them, then the multiplication also belongs to R2. So that's all this property is trying to say. And cu also belongs to R2. And condition checks. In the same manner, similarly, we can easily verify other, how many remaining? Other 4 conditions. 4 axioms, like we call it. Axioms. So R2 is a vector space. So now you got the idea how to check whether the given space is a vector space or not. So how we define vector space is that a space whose objects satisfy all those 10 conditions will be a vector space. If it failed any one of the 10 conditions, if it just failed one condition out of 10, then that cannot be the vector space, okay? But every time checking those 10 conditions is too much work, okay? It's not fun. So what we want to do now is that we want to try to make it short and easy to work with, okay? So from now onwards, what I will do is, at this moment, I say that a vector space that satisfies these three conditions, condition number 1, condition number 4, and condition number 6. Any space that satisfies those three conditions will automatically satisfy all the remaining conditions. Guys, let me repeat this. A space that satisfies these three conditions. What are those three conditions? Closure under addition, which means if u and v are two vectors and u plus v also belongs to the same space, we call it closed under addition. Another axiom is there is a zero vector, and another axiom is multiplication by a scalar. If the space satisfies those three conditions, then it will automatically satisfy all the other conditions. We'll prove that, we'll discuss in more detail later, but at this moment, just remember at least those three conditions. What are those three conditions again? Closed under addition. And there is a zero vector. We call it additive identity. Another is closed under scalar multiplication. You consider one scalar and you multiply that with the vector, and the multiplication, the result, the product will also lie on the same space. And with this in mind, let us prove maybe one or two examples here. Let's look at example 4. All right, let's look at example 4. In example 4, as you can see that Pn represent the set of all polynomial of degree at most n. You know the polynomial, right? Polynomial means you have learned that in high school. Let's say y equals, let's say, 5x power 4 plus 3x cubed minus, let's say, plus 2x minus 1. These kind of function, these kind of equation are called polynomial. This one is polynomial of degree 4. X squared minus 3x plus 1. This is a polynomial of degree 2. We call it quadratic equation for polynomial of degree 2. So if we have y equals x minus 1, for example, this is a linear equation and the degree is 1. We call it polynomial of degree 1. Okay, it is a polynomial of degree 1. So I trust that you are familiar with the polynomial of degree. So the pattern of the polynomial is this. The standard general form of polynomial is, if I write p of x, that will be some constant, okay, and a1x plus a2x squared plus a3x cubed plus all the way up to a n xn. So this is called the polynomial of degree n, because the highest power in the polynomial is n. Generally speaking, for polynomial, instead of x, we'll be using t, okay? So the same thing, I generally use t as a variable. So a0 plus a1t plus a2t squared plus all the way goes up to an tn. So our variable, we generally consider t as a variable to represent the polynomial in general form. Now, in this example, what we want to do is Pn is represent the set of all polynomial of degree at must n. Okay. Now we need to show, is it a vector space or not? That's we want to check. Okay. As I said earlier, instead of those 10 axioms, 10 condition, 10 rules, we will just verify those 3 rules out of 10. All right, if you want to show all of those 10 rules, that's okay. I don't have any problem. The only thing is you may have problem, right? It'll take lots of time. So I suggest just use those 3 property, 3 axioms I mentioned earlier. So axioms number 1. Okay, here we just, I think I have already written there. Yeah, we justify or we verify 3 condition, 3 axioms. Why 3 axioms? Again, if the space satisfy those 3 conditions, it will automatically satisfy all the remaining conditions. We can prove that easily. So condition 1. Okay, so closure under addition. Closure under addition. From now onwards, I simply write just addition after that maybe. Anyway, I'll just write this one right now. Remember, what we need to do is we need to consider at least 2 vectors and 1 scalar for this. So let's do this. Let P of t is an Pn of t, and anyway, let's consider 2 vectors. Okay, let P and Q belongs to Pn. This one is, remember, I consider this a lowercase p and this one is a uppercase p. So I resolve that uppercase p to represent the set of polynomial, but this is a vector. This is one object in that space. Okay, imagine that this Pn is a container and all of the objects in this container are just of this form, this type. Okay, where P of t or P of x, doesn't matter what variable you want to choose. P of t, we can write this as a naught plus a1t plus a2 t square plus all the way to a n tn. And q of t is another object in that container, another polynomial. So let's say this is b naught plus b1t plus b2t square plus all the way to bn tn. Okay, guys, some people find it confusing, then please listen very carefully. And if you have any questions or concern, let me know right away, okay? Now, we need to show that it's closed under addition. That means we need to show that P of t plus Q of t also belongs to Pn. Let's see what happens. P of t plus Q of t equals P of t is a naught plus a1t plus a2t square plus all the way an tn plus Q of t is b naught plus b1t plus b2t square plus all the way up to bn tn. Now I can write this as you know, the constant term a naught plus b naught, they are constant, and I want to take t common. So if I take t common, what is left over is a1 plus b1 plus, in the same way, I want to take t square common, you'll get a2 plus b2 t square plus all the way up to an plus bn tn. And clearly, this belongs to Pn, right? Because this is also a polynomial of degree n. So the coefficient may be anything, it doesn't matter. Clearly, P of t plus Q of t belongs to polynomial of degree n. So condition 1 checks. Closure under addition is done. Now the second condition is zero vector. Okay, second condition is zero vector. We need to prove that zero vector is in Pn. So can you tell me whether 0 belongs to Pn? 0 can we write 0 in that form? So we know that 0 can be written as 0 plus 0t plus 0t square plus all the way up to 0tn, right? So this 0 is also a polynomial of degree n. So clearly, 0 is also a polynomial of degree n, so it belongs to Pn. So this also checks. Okay, so that if you add any vector, P of t plus 0 will be P of t. There is no issue there. As long as you prove that 0 is in the container, 0 in that space, then you are done in the second condition. So you don't have to show that. Just show this. So condition 2 checks. 0 is in P2. Now the third condition is scalar multiplication. Okay, close under scalar multiplication. So we need to show this, whether it is closed under scalar multiplication or not. All right, so let's see. Let us suppose that C is a scalar, be a scalar, and I think we have already defined P there, P and Q already defined. We just consider C as a scalar. Now, C of P T also belongs to P, and that's what we need to prove. So C of PT equals C of, this one is A naught plus A1t plus A2t square plus all the way AN TN. So I can write this as A naught C plus A1C T plus A2C T square plus all the way up to ANC Tn. So clearly this belongs to Pn, because remember, it is a polynomial of degree n with the variable t, because these all are constant. I mean the scalar. This one is scalar, they are just the coefficient, so this belongs to Pn. So therefore this condition also checks. Okay, since it satisfies all those three conditions, since Pn satisfies all the three conditions, Pn is a vector space. All right. Now you can prove all the other 7 conditions if you like, but you don't have to. Okay, you can prove it just for fun. I don't have any problem. Let us define vector subspace. What is a vector subspace? Okay, here is the definition. A subspace of a vector space V is a subset H of B that has three properties. The first property, one of the three properties, is the zero vector of V is in H. H is closed under vector addition. That means if U and V is in H, H is a container, U and V are its objects, okay? Then the sum U plus V also belongs to H. So this is, I think, this means this part B is actually the condition 1 that we have seen earlier. It is condition 1. This one is condition 4, okay, axiom 4, zero vector. And this one is condition 6 or rule axiom 6. Axiom 4, axiom 1, axiom 6. If a space satisfies those three conditions, notice that V is a vector space and H is a subset of V. I believe you know what is the meaning of subset. So H can be equal to V or less than V. It cannot be greater. So H is a subset of V. H is taken out of V. Okay. So then if H satisfies those three conditions, then this is called subspace. And that's the reason why we use those three conditions earlier. And if it is a subspace, then it is automatically a vector space by itself. Any subspace itself is a vector space. Okay, here is the some notes here. I think you may want to read. Properties A, B, and C guarantee that a subspace H of V itself is a vector space. Okay, every subspace is a vector space. Conversely, every vector space is a subspace of itself and possibly of other larger space. Okay, to prove that a subset H of a vector space V is a subspace of V, you need to show that these three properties are satisfied. If one of them is not satisfied, or if the vector space, whatever the space is given, and if it fails any one of these three conditions, then it cannot be subspace, therefore it cannot be vector space. We just need to check those three conditions. Now, if you believe that a subset H of a vector space V is not a subspace V, it is enough to find one counterexample, one example showing that one of the three conditions actually is not satisfied. So too much talking. Let's look at some example. I think I will go first. Let's work on example 6 first. Let H be the set of all vectors in R3 of the form xy 0. You know that xy 0, it can be written as xy and 0. Is H a subspace of R3? Why or why not? So we need to check those three conditions. All right, guys. Okay. If you know how to do one, I think you can do the pretty much all the problems in the similar manner. So solution. Here we need to verify three conditions, axioms or conditions. Condition 1. Let's begin with zero vector first. Whether it has zero vector or not, okay? 0 can be written as 0, 0, 0, right? We can write that. If we suppose x and y 0, x and y are variables, so we can choose anything. If we choose x equal to 0, y equal to 0, then we get 0, 0, 0, which belongs to H. Remember, H is a container, okay? H is a container, and all of the objects of this are of this type, x, y, 0. That means 1, 2, 0 may be the object in that container, 2, 3, 5, 0 may be the object in the container, 0, 1, 0 may be the object in the container, 0, 0, 0 is also in the container. But if you write 1, 2, 3, it cannot be in that container because the last term is 0. So you cannot substitute 0 by any other number. But x and y can be substituted by any value. Okay, so 0 belongs to H. If we suppose x equal to 0 and y equal to 0. So clearly 0 is in H. Second condition. Let's say addition, close under addition. Let's check that. Closed under addition means we consider two vectors u and v, and we need to show that u plus v also belongs to H. U belongs to H, v belongs to H, and their sum also belongs to H. That's all we need to show. Okay, so let us suppose that u belongs to H. And v also belongs to H, where u equals, let's say, u1, u2, and 0. And v is, let's say, v1, v2, and 0. Okay, this is the type, x, y, 0. So x and y, you can suppose any number, any value, anything, but last term must be 0. Okay, these are u and v. Now, our job is to show that u plus v also belongs to H. So u plus v will be u1, u2, 0 plus v1, v2, 0. And that's going to give me u1 plus v1, u2 plus v2, and 0. Clearly, this is, this object is similar to xy 0, right? u1 plus v1 is some number, just like x. u2 plus v2 is also another number, just like y. And the last one is 0, therefore this belongs to H. So the condition 2 also checks. Okay, now let's try condition 3. Condition 3 is closed under scalar multiplication. Scalar multiplication. Let's see what happens. So let us suppose u is in H and C be a scalar. Then Cu equals, Cu means u1, u2, 0, which is Cu1, Cu2, 0. Clearly, this belongs to H, right? It is also of this form, xy 0 form. So this also checks. So since H satisfies all the three conditions, H is a subspace. Of R3, because whatever the object that we consider x, y, z, x, y, 0, this actually belongs to R3. So R3 is a bigger space, bigger container. R3 contains x, y, z, these kind of objects, right? It could be 0, it could be any number, negative, positive, doesn't matter. That's where the R3 actually is. R3 contains. But x, y, 0 is just a small chunk of R3, and we denote that by H. and we prove that H also satisfies all those three conditions, therefore it is a subspace. Okay, so example 5. So we're given H and the objects in that H container are of this type, non-negative. Now each H a subspace of R2. Why or why not? Now let's check zero vector. We need to check three conditions. Condition 1, zero vector. Is zero vector is in, remember the objects 0 and 0, 0 clearly is in H, because remember here H has all the type, it is not F, just XY, okay? So X and Y type, all the objects of this type. So X and Y, you can choose any value which are non-negative. See here, there is a condition. X is greater than 0, Y is greater than 0, greater than or equal to 0. So we can consider 0, 0. Now, just in case, if the question is X is greater than 0 and Y is greater than 0, then you cannot consider 0, 0. Therefore, it violates the condition 1. You can say directly that it does not satisfy condition 1. Therefore, it is not a vector space. But in this case, 0 can be considered. So 0 is in H. Condition 1 checks. Now, condition 2, let us check close under a scalar multiplication. Let's see what happens. Let us suppose that U belongs to H. Where? Because H is a subspace of R2, therefore U must be of this type. So U will have, U is a vector which is denoted by this way. Okay? U is in H, and since H is a subspace of R2, the object will be of the form U1 and U2 like this, where U1 must be, see here, there is a condition. None of the objects can have negative value. So U1 is greater than 0 and U2 is also greater than or equal to 0. Okay? Let us suppose C be a scalar. Where, let's say C equals -1 or -2 or -3, whatever. Then what happens? Then Cu equals C is -1 times U is U1, U2, which is negative U1 and negative U2. And this does not belong to H, because H cannot have any negative numbers there, right? So now we notice that if we try to use this property 2 close under scalar multiplication, and if I suppose C equals to -1, then what we came up with is that there are negative values there. But if there is any negative value, it cannot be in H, because H is defined this way. All right, which is not in H. So H is not a subspace. We don't have to check the third condition. We already saw that, the second condition actually failed, so you don't have to do the other one.